Huh? Alright, so what do I want to do about this AP Physics final project? Well, I could do a lesson, escape room. Nah, I could do physics and movies, but like, nah, my favorite movie is like Big Hero 6, and that's not even, that doesn't even count. Physics of sports? I mean, nah, I guess that could work, but I mean, I swim. I mean, I guess I could do a lesson, but what would I do it about? Hardest physics topic, quantum mechanics. You know, that'd be pretty funny if like I did my AP Physics final project on like the hardest physics concept like ever. So I'd like to preface two things before I go on. Number one, quantum physics and quantum mechanics are the same word. They're interchangeable. So within this video, I'm gonna use them both. It took me 2 minutes to realize that there's no difference at all, and I will never get those 2 minutes back. The second thing I'd like to say is that quantum physics really makes no sense. So I'm not really an expert. So if you are interested in quantum physics, please ask an actual expert on it, not me. Now that we got that out of the way, quantum physics describes the smallest things within our world, like atoms, molecules, protons, electrons, etc. And you might be thinking, atoms, molecules, isn't that just chemistry? Not at all. Not the same thing at all. Chemistry is how atoms and molecules combine and interact, and it's how they create elements and all that. But quantum physics is the study of the properties and behaviors of atoms and molecules. It's always what are atoms and never how are atoms. Take a look around you. Try to find an object with atoms. Spoiler alert, they're everywhere. Atoms are everywhere. So technically we are made up of quantum physics. So in chemistry or in any other science, we draw particles like this. Very circle, spherical objects. But in quantum physics, we draw particles like this. This is an electron. And this is what we call a wave function, or waves. Now these wave functions are abstract mathematical waves. But to get the physical properties of these wave functions, we have to do some math. So let's say we're trying to find the position of an electron. We take the amplitude and we square it, and it'll look something like this. And so in quantum physics, there's this thing called probability distribution, where we'll most likely find an electron at the top of the wave rather than the bottom of the wave. And so I say probability because we can only really predict with quantum mechanics. We don't really know anything to a certain degree, or to a certain level, or to a definite detail. And the wave function model is really good at predicting what molecules and atoms will do. But we don't even know if it's real or not. We haven't even seen it. All we see are these particles. But you know what they say? You can't see the wind, but you can feel it. I don't know how that relates, but... And so these waves are hiding from us, almost in this quantum realm. And within this quantum realm are where the waves are. And in our world are where the particles are. And it's almost like there's this barrier between this realm and our world. And this barrier is dubbed the measurement barrier, where the waves collapse into particles. Now you might be asking, how do waves collapse into particles? I don't know, and that's okay, because physicists don't even know how they actually collapse. That's called the measurement problem. The inability for us to observe how waves collapse into particles. Whew. Dang, Koji, that was a lot of words said in a lot of minutes. No way there's more about quantum physics. You'd be wrong. So put on your seatbelts because it's about to get really, really weird. So superposition is a concept in quantum physics where two particles or two waves can be at the same place at the same time. It kind of looks something like this. Think about it like this. You drop two rocks in a pond. Those rocks will create two different waves. And when those two different waves interact with each other, they create one really big wave. And so technically within quantum physics, those are just two waves at the same place. But not only are they at the same place at the same time, they're also doing two different things at once. For example, with electrons have a positive and negative spin. That's what they call the spin state. And with superposition, electrons can both have a positive and negative spin at the same time. And a lot of physicists say that these electrons exist in multiple states or multiple places until we observe them or measure them. Then they collapse into one place, in one state. So this led many physicists, like Aaron Schrodinger, to create thought experiments. The most famous being Schrodingers Cat. Now Schrodingers Cat is where we put a cat and a vial of poison in one box. A little dangerous, I understand, and this vial of poison is meant to go off at any time. It's very unpredictable. We don't know when it'll go off. And so this cat in a box is simultaneously alive and dead at the same time. Until we open the box, then it becomes dead or alive. The point of that experiment was for Schrodinger to say how absurd superposition was in quantum physics, and that it really made no sense how two things could be at the same place at once.
Yeah, so I might be wrong, just a little smidge though. So within Schrodinger's lifetime, they did prove superposition through the observer effect, and the observer effect is real. Just a quick summary: the observer effect is that since we observe something, we change it, like the two particles becoming one particle. And so Schrodinger did believe in superposition. He was just like, that's kind of dumb, that's kind of stupid. Like, even though it makes sense in the microscopic field, doesn't make sense in the macroscopic field. So he made this experiment, the Schrodinger's cat experiment, to show that if we look at the cat, did we really kill it? Did us observing the cat really kill the cat, or was it the vial of poison that was in the freaking box? So it's kind of like he made a meme, but like in an experiment. I just go back to the...
And so now there's quantum entanglement. Quantum entanglement is when two electron waves are deeply connected with each other, whether by interacting or sharing spatial proximity. Their spin states, remember when I said positive and negative spin, their spin states become entangled, meaning that these two electrons that are entangled can only have opposite spins, meaning that this electron can only have an upward spin and that this electron can only have a downward spin. And the craziest part is, if you were to put these two entangled electrons far, far apart from each other, like ends of the world apart, if the spin of these electrons are entangled in such a way, if we measure one electron and that electron shows that it has a positive spin, then we immediately know that the other electron far, far away from it has a downward spin or a negative spin. Think about it like this. Let's say you go to a restaurant and you order a hamburger and a hot dog. And once they give you the food, they give you the food in like a little white styrofoam, you know what I'm talking about? Now you don't know which styrofoam box has the hamburger or the hot dog until you open up one. Let's say you open up one and it has the hamburger. Then you immediately know that the other one has a hot dog. I'm just really hungry. It's like 9 p.m. and I haven't had dinner yet. In order to understand quantum tunneling, we have to understand that particles do not have a defined position. Obviously until they're measured, of course. Now in the real world, see I didn't go through the wall? That's because it's regular science. There's like matter and stuff in this wall that will make sure the lunchbox doesn't go through the wall. If it does, then we have a problem here. But in quantum physics, electrons have a probability of moving through a wall, which is crazy because like how is that even possible? Like what? When a wave function meets a barrier, it'll decay exponentially. But if the barrier is not too high or not too wide, then there is a probability that that wave function will extend to the other side, meaning that there's a chance that an electron will pop up within that other side. And this goes back to probability distribution. Since there's a wave on the other side, there's a probability that when a measurement is made, an electron will pop up on the other side of the barrier. So in theory, electrons have a probability of moving through a barrier or moving through a wall if the wall is narrow enough. And the last important concept I'm going to talk about is the Heisenberg uncertainty principle. So a wave function tells us everything we need to know about a particle, like its position or momentum. Now to find the position of a wave, we use the amplitude of the wave, but to find the momentum of a wave, we have to use the wavelength of a wave. Now take a look at this wave. How are we supposed to find the momentum if it has a bunch of different wavelengths? Hear me out here, let's use a sine graph. Now the sine graph has equal amounts of wavelengths, so the momentum will have a precise value. But in doing so, the amplitude is also the same. So there's an equal probability of the electron being anywhere out in the universe. That means there's an uncertain value to the position of the electron. And although we alleviate the uncertainty of the momentum value, we just increase like what the heck is the position. Now let's look at position. Let's try to find a certain value for position. We can use this. Only one position in the graph. But then what the heck is the momentum? Because there's an unequal amount of wavelength. And so that is the Heisenberg uncertainty principle. So even though we can find a precise value for momentum, we will have an uncertain value for position. Or if we find a precise value for position, we can't find a precise value for momentum. When I first heard about the Heisenberg uncertainty principle, I was like, dang, that's Breaking Bad type stuff. But Breaking Bad is also chemistry, and that's for cowards. So remember when I said that like the last thing we're going to talk about is the Heisenberg uncertainty? No, that was a lie. We're going to talk about the many worlds interpretation, otherwise known as the multiverse. Created by theoretical physicist Hugh Everett, every time a quantum measurement or quantum observation occurs, usually it collapses into one state. But Everett suggested that it just branches off into different worlds. So the universe just branches different copies of worlds, which each follow through a different outcome of a measurement. So let's go back to the cat that be dying and stuff. Schrodinger's cat. At the moment of measurement, or when we open the box, the universe splits into two different branches. One branch or one world where the cat is alive, and one world where the cat is dead. And now each branch represents a different outcome. The cat is alive, the cat is dead. And they both exist simultaneously, but also being separate but parallel worlds. And then with the many worlds interpretation comes quantum immortality. Quantum immortality is where our conscious will follow through the branches where we continue to survive. So let's say I'm driving my car and then I crash. Now there are two different branches of the scenario. One where I don't crash, and one where I do crash. And so my consciousness will go to the branch or the world where I survive. And so from the POV of the person's conscious, it will always just continue to go to the branch or the world where we continue to survive, meaning that we are technically immortal. Now just a disclaimer, this is all just an interpretation, just a theory, and that this is not actual literal immortality. It's all just science fun, you know what I mean? So today, I'm gonna do a demonstration on quantum physics. Now you might be asking, oh my gosh, are you gonna split the atom? No. The next best thing. I'm gonna recreate Schrodinger's cat. Now, I don't have a cat, but I do have a dog. Everyone, this is Chiro. Say hi, Chiro. Okay, so what do you do if your subatomic car breaks down? You take it to the quantum mechanics. So my dog doesn't really like me. He doesn't have the greatest passion for me either, but it's okay. And let's see how long it takes before he attacks me. So if you don't remember, Schrodinger's cat is where we put a cat in a box and we put a vial of poison in a box. And then the cat is simultaneously alive and dead through the superposition of quantum physics. Now I don't have a vial of poison and I don't know where to find a vial of poison. So I also have the best next thing. I have a bomb. And so this bomb represents the random vial of poison. We're gonna tape this bomb. Try doing this with one hand. Don't eat the tape. We're gonna tape this bomb on Chiro. Okay. Alright, Chiro. Get in the box. Get in the box, Chiro. Get in the box. Bomb. So pretend this box is closed, right? Now in superposition in quantum physics, my dog here would be simultaneously alive and dead. Until we open this box, then my dog would be alive or dead. So let's open the box. Oh my god, he's alive! And the bomb didn't go off. And that's Schrodinger's dog. Or Kojinger's dog. That was really dumb. What?
I'm sorry. It's okay. Get some nice shots of him real quick. Oh yeah.
Now I have to find a mathematical relationship for quantum mechanics in AP Physics 1. So I kind of screwed myself over with picking quantum mechanics because quantum mechanics and AP Physics are two very different concepts. But luckily I found Schrodinger's equation, baby. Let's go! Now it looks super scary, and it does because it has the Minecraft trident in the equation, but it's not that bad. I'll explain it to you. So the H, little weird H symbol on there is the Hamiltonian operator. It symbolizes both the kinetic and potential energy of the system. And the big E over there is just the total energy of the system. And the little Minecraft trident is the wave function of a particle. Now I don't know if you guys see this or not, but it's just energy equals energy. Let me think. What top? Conservation of energy. Conservation of energy, baby. And so energy is only conserved in a closed quantum system. Energy is only constant when there are no other external factors that disrupt this system. Let me think. How does that relate to AP Physics 1? Mechanical energy is also conserved in a closed system. Remember all those little experiments we were doing where we had to find the conservation of energy? It's all those multiple choice questions where it says friction is negligible. It's only to show that conservation of energy exists. And so yeah, thank you guys for listening to my really boring lecture on quantum mechanics. I spent a good like 10 days trying to figure out what it all means, and I still am no expert, and that's okay. Thank you. I hope you guys learned a lot, and yeah, stay healthy.